Hi, good evening. Akshit, so are you able to hear me and see my screen? If you're not able to unmute, you can just give a thumbs up. Yeah, sure. Hi. Okay, so then we will just start now. Mhm. Okay, so good evening once again, and welcome to this problem solving session for week 6. So in this session, we will be covering problems on the regulators, that is linear regulators. So this week you went through linear regulators, you had an introduction to that, and you also saw its various performance parameters. So that is how you evaluate different regulators based on the line regulation, load regulation, and of course the temperature dependency. Correct? And broadly, you saw that linear regulators can be classified into two, that is the shunt regulator and the series regulator. So you saw the operation of both the circuits, correct? And specifically for shunt, you went through its applications, that is voltage reference generation and current regulator, correct? So you saw that the voltage reference shunt regulator is used in the um, making of series regulator as well, correct? And in series regulator, you went through its operation, then you saw two special categories, that is the negative voltage regulator and the dual voltage regulator, wherein you have both the positive as well as negative voltages getting regulated. Okay, and in addition to that, you also went through how to do overcurrent limiting using the conventional circuit, as well as you have the foldback limiting circuit. And you also saw some improvements to the series regulator, which can help you achieve better regulation. Correct? So before we go through the problem solving session, I'll just quickly recapitulate whatever was taught in the sessions. So that will provide us the basis towards solving problem solving, right? Okay, so I'll just turn on my pointer over here. Yeah. Okay, so all of these slides are based on whatever was covered in the lecture slides as well. So it's just a recapitulation of all the slides that was covered in the lectures, right? Okay, so you saw that the idea of a DC-DC regulator is to actually have a fixed V naught at the output, correct? For instance, if you have 230 volt AC, so 50 hertz sinusoidal source at the input side, what you typically do is you have a transformer with a turns ratio of, let's say, 1:n, and then what you do is you try to rectify it. So what is used over here is actually a full bridge rectifier, diode based full bridge rectifier. And of course, you know that if you don't have any filter at the output, you will get a rectified sinusoid at the output, right? It is a DC, however, it's a pulsating DC, correct? So that is something you don't want. What you want is actually a flat DC, correct? So what people typically do is they have a capacitor filter at the output. So in the last week, you went through this elaborately. That is, if you have a capacitor filter, you of course know that it is going to draw some inrush current, correct? So in case of that, how you limit the inrush current, right? So you saw different mechanisms starting from resistive inrush current limiter, and then the potentiometer based inrush current limiter. Then you went through the MOSFET based inrush current limiting mechanism, and then you went through the transformer based inrush current limiting, and finally you went through the relay and contactor based inrush current limiting. You also saw that relay and contactor mechanism was the best amongst them all, because it was able to give you a resistive inrush current limiting at the starting, and as the number of cycles go on, or as the capacitor gets charged up, the resistor is bypassed using a relay and a contactor mechanism, correct? So you went through that in the last week, correct? So now we will assume that this entire part has been replaced by a single DC voltage source called VI. And of course, you know that you have just limited the intercurrent and you have, let's say, almost a flat DC, but you know that it's not a flat DC, correct? Because it will still be a pulsating DC. However, since you have a large capacitor over here, you assume that it is almost more or less DC, but it's not exactly DC. That is why it has been called VI unregulated. Okay. So what we want is a V naught regulated value, and this value may change. Correct. So let's say you have a 15-volt input. I would want an 8-volt output or a 10-volt output or 12-volt output or so on, depending on my application. So this is where my DC-DC linear regulator comes into play. Okay. So with this as the background, you went through different types of linear regulators, that is shunt and the series regulator. Okay. Right. And based on the regulation mechanisms, you also kind of understood how to evaluate different regulators. You will also see a problem on this. That is, you understood that there is something called as a line regulation, there is something called as a load regulation and temperature regulation, which is based on whatever is the delta VI, that is whatever is the change in the unregulated DC input, correct? So if you have a change in unregulated DC input for, that is a delta VI, how good your V naught is maintained at V naught. Okay. So let's say I have a change in input from 8 volt to 12 volt. How good am I able to maintain my output voltage at 5 volt? Okay, for this variation. Similarly, you have variation in R naught, that is your output impedance, right? You know that the output impedance may vary from 0 in case of a short circuit to infinity in case of an open circuit. So what is the range of R naught which would allow you to have a fixed V naught at the output? So that is your load regulation, correct? And finally, you have the temperature regulation, that is, it mentions the susceptibility towards temperature. So you know that delta V naught, that is the variation in the output voltage, is a summation of all of these three, correct? That is dou V naught by dou Vi, that is a line regulation coefficient into delta Vi, plus dou V naught by dou I naught, load regulation coefficient into delta I naught, plus dou V naught by dou T, that is temperature regulation coefficient into delta T. So this should give you the what is the change in your output voltage, correct? Okay. Let me just check once over here. Right. Okay. So you went through shunt regulator in detail. That is, you understood that in a shunt regulator, you have the VI, that is the unregulated DC input, and then you add a series resistance to that. Okay. And across that, you will have a Zener diode. Okay. So this Zener diode, as you would have understood from the operation of a Zener diode in your analog circuits as well, you know that it has an avalanche breakdown at a particular voltage called VZ. So that is called the Zener breakdown voltage. So the idea is that irrespective of the Zener current, irrespective of IZ, you have a fixed voltage coming across the Zener diode. So you purposefully operate the Zener diode in the third quadrant, correct? You purposely operate it in the third quadrant, and you see that, okay, I'm able to maintain a fixed VZ across the Zener. Okay, so I'm able to maintain a fixed VZ, and this is actually getting reflected as V naught. Okay, you have the load over here, R naught. So across the load, you get obviously a fixed V naught, VZ. Okay, so the idea is your VI is varying from VI min to VI max. Your load may vary from R naught min to R naught max. However, I would want a fixed V naught. Okay. However, there is a bottleneck in terms of the Zener diode, in the sense that the Zener diode can, ideally, of course, it needs to have a fixed VZ for all values of current. However, you would see that it has a specific IZ minimum, IZ maximum, okay, within which it maintains a fixed VZ. Okay, so what is this IZ maximum? If you go to the typical data sheet of any Zener diode, they would give the power rating of the Zener diode. Okay, or that is the power dissipation. Therefore, you cannot expect a Zener diode to maintain a fixed VZ for very high values of current. Okay, what would happen is the power level would get exceeded and the Zener diode would blow. So this is the bottleneck, or this is the design criteria for the Zener diode. That is, your IZ max should be less than or equal to PZ by VZ. Okay, that needs to be ensured at all points of time. That is, IZ should be less than or equal to PZ by VZ. So based on that, your load may also change. Okay, right. And you also studied the efficiency of such a voltage regulator. That is, your efficiency, which is your output power divided by input power, can be written in terms of the input output voltage differential, that is Vi minus V naught. So you saw that the efficiency is actually indirectly proportional to delta VA naught. That is, if your delta VA naught is higher, you obviously know that your efficiency is going to be lesser. That is, if you have a very wide variation between your input and your output, efficiency is going to be lesser. It also makes sense, right? Because if you have a very wide variation, it means that a large amount of drop is going to occur across this resistor RS. So that would result in I square R loss across this resistor. Therefore, if you have a wider variation between Vi and V naught, that is going to be a larger drop across this RS, and that will be the cause of um, fall in efficiency. Okay, so this is about your shunt regulator. Okay, so then what you did was, okay, so this is your ideal circuit. Then what you did was, okay, so let's replace the Zener diode with a practical Zener diode, right? You of course know that a Zener diode has an Eisenmin and Eisenmax, but more than that, what you see is that it may not be a fixed VZ. Okay, the VZ may have a particular slope over here. Correct? So you understand that since this is a VI curve, VI characteristic, the slope would actually give you the resistance, or in this case, 1 by RZ, right? That is 1 by RZ is the slope of this curvature, right? So you know that the Zener diode can now be replaced by a DC voltage source and then RZ in series, right? So you see that the Zener is no longer able to maintain a fixed VZ, rather it is now going to have a voltage which is VZ plus IZ RZ. Therefore, your Zener current is going to actually play a huge role. If your Zener current is higher, you see that V naught is also going to be higher. Okay, so you see that this IZ RZ term is the one that's responsible for loss of regulation. Okay, so we need to reduce this particular term to improve regulation. How do we do that? Right? So that is where, so idea is you want to reduce IZ as much as possible, or you want to reduce the load on IZ as much as possible. Okay. So what we did was we connected, or we modified the shunt regulator by connecting a BJT, NPN transistor. So in this circuit, you saw that your V naught is equal to VZ plus IZRZ minus the VB drop across this transistor. So that is your V naught. But more importantly, what is your IZ now? You see that for the Zener, the load is now going to be simply the base current of the BJT, right? And base current of BJT, as you know, is very small. In this case, that is I naught is the collector current, emitter current. So I naught by beta plus 1, that will be IZ, right? So your IZRZ is going to be much, much reduced. Okay, so this is your modification in your shunt regulator in order to have better regulation, in order to compensate for this IZRZ drop. Okay. But more importantly, we went through its applications, right? So one is to give a fixed voltage regulation. That is, the same circuit has been redrawn in this fashion. So you understand that if you vary this potentiometer, right? This is a potentiometer across the Zener diode. If you vary this potentiometer and take a tap out of its point, you see that you get a fixed reference voltage, right? Reference voltage need not be just the VZ, it can vary anywhere between 0 to VZ, right? So you see that you are able to get a voltage reference between 0 to VZ, a variable DC output you are able to get, controllable DC output, correct? So you can also do a closed loop control in order to get some particular value of Vref or maintain a particular value of Vref. and that has been used subsequently as well. So another reference or another application is your current regulator, right? So in the same circuit, what was done is a BJT and a BJT with its emitter resistance was added, a PNP BJT, and of course the collector is connected to this load. Okay. In this case, the idea is that your VZ is constant over here. Therefore, your VRE is going to be constant because Vz is constant, so Vz minus Vb will be your Vre. Therefore, for a fixed value of Re, IRE is going to be constant, right? Or IE is going to be Vre by Re, or Vz minus Vbe divided by Re, which is a constant, right? Therefore, since your emitter current is constant in a BJT, collector current is also constant, right? And you know the relation, right? I naught is IE into beta by 1 plus beta. Okay. So these are the two applications that you saw, and you came to series regulator. So then you came to what is known as a series regulator, right? That is, you simply have two resistors in series, and one is actually a potentiometer, that is RS is a potentiometer, right? And the heart of the circuit lies in this closed loop action, correct? So you sense what is your V naught, and you have a fixed V naught reference that you want at the output. So you sense what is the actual V naught, you give the actual or you give your reference value and you subtract it. In ideal scenario, you want your V naught reference to be same as V naught, right? That is, your output voltage should be the same as V naught reference. Your output voltage should actually track whatever is your reference voltage. If there is an error, there will be a finite error E, that is V naught reference minus V naught. There will be a finite error. And based on this error, the RS is varied so that V naught comes back to V naught reference. Okay, so it is a closed loop negative feedback system, right? So the idea is that if, let's say, your V naught increases, then V naught is higher than Vref, then let's say error will decrease based on that because your V naught actual is higher. Error decreases, therefore your RS value is increased so that a greater drop occurs across this RS, and across V naught you have a lesser voltage. Okay. So, however, you understand that this is a very lossy circuit, right? Because you have two resistors and there's going to be a drop across this. So, why don't we replace this RS with a BJT, right? Because in BJT, if I can control VCE, that will constitute the drop. Okay, right. And for this circuit as well, you saw the efficiency calculation. Again, you understand that if your delta VI naught is higher, your efficiency is going to fall. Correct? Okay. So this circuit is a modification to the previous circuit that we just saw. That is, you have replaced RS with a BJT based circuit. Okay. So you have Q1, which is kind of your power BJT, right? And you control the drop across Q1, that is VCE1. Okay. So based on my V naught, I need to control VCE1. That is, if you want your V naught to decrease, then VCE1 should increase. So there is a greater drop across VCE1, therefore V naught decreases, or vice versa. If you want your V naught to increase, then the drop across VCE1 needs to decrease. So to control this, you will control the base current of Q1, right? So you control the base current of Q1. Fine. And one more addition to the circuit is, okay, so how do we control the base current of Q1? So again, for that we use a BJT, and in this case, the BJT is operated as a current controlled current source. Okay, fine. So what do we do over here is, let's say I will maintain a fixed VZ across the emitter terminal of this NPN transistor. Therefore, your emitter voltage or VE will be equal to VZ or V naught reference, right? And you sense what is your output voltage and you take a tapping out of that, right? Using a resistive divider, which is C into V naught. So a voltage difference of a V naught and V naught ref occurs across the VBE terminal, right? So you understand that. So if your V naught increases, then the drop across this VBE is going to be higher and vice versa. Okay. So this is kind of your feedback mechanism, or this is your subtraction mechanism. That is, AV naught is your sense voltage and V naught ref is your reference voltage. Okay. And based on this error, your IRB varies. How? You see that IRB over here is equal to VI, which is the voltage over here, minus V naught plus VBE1, right, divided by RB. Correct. So, and you also know that since your IRB is more or less constant, if you assume that VI, V naught, and VB are all constants, your IRB is constant. Therefore, if IC2 increases, your IB1 decreases, and vice versa. Correct. This is your IC2. So the current entering to this terminal, if IC2 increases, then IB1 decreases and vice versa, right? So let's take a test case. That is, if your V naught increases, you know that AV naught increases, correct? So AV naught increases. So AV naught goes more than V naught reference. Therefore, you will see that IC2, correct? Since your AV naught is more than V naught reference, there will be a more base current over here, more base current flows. Since more base current flows, IC equal to beta IB, therefore IC increases. That is why IC2 increases. So since your IC increases, IC2 increases, IB1 decreases, correct? Because your IRB is constant. Therefore, IC2 increases, IB1 decreases. So if your IB1 decreases, right, you're giving lesser base current to Q1, correct? So if your IB1 decreases, your drop across this transistor is going to increase. Correct? The transistor becomes more and more lossy. Drop across this transistor increases, therefore your V naught decreases. So this is your negative feedback. You can also do the other way. If your V naught decreases, then AV naught decreases. Therefore, you will see that the base current of Q2 decreases. Since base current of Q2 decreases, the collector current also decreases. Since IC2 decreases, IB1 increases. If your IB1 increases, the transistor will conduct with lesser drop, right? So VCE1 reduces, therefore VCE1 reduces. Since VCE1 reduces, V0 increases. Okay, simple operation, right? It's a very good feedback and correction mechanism implemented using BJTs. Okay. Okay. So you saw the basic operation of the series regulator, and one modularity that you can incorporate in the circuit that you saw was that instead of having positive voltage, you can also do the same for negative voltage, right? Let's say you have a negative 15 volt and you want to make negative 10 volt, right? You just flip your DC voltages and make your NPN to PNP transistors, flip your Zener diode, and that's it. Okay, this is your negative voltage regulator. Now that we have both positive and negative voltage regulator, you can combine both of them and get a dual power supply linear regulator, wherein you have a common ground, right? So you give a plus 15 and minus 15 supply, or rather you give a plus 15 and minus 15 supply to the input, and using these two regulators, you get a plus 10 and a minus 10 with respect to a common ground. Okay, by combining both the positive voltage regulator and negative voltage regulator. Okay. So now that you have seen the operation of or understood the operation of both circuits, you saw some more current limiting mechanisms that you incorporate as well. So in the series regulator circuit itself, we incorporated a current limiting mechanism based on a third BJT, right? So this is again in the NPN an NPN transistor. The idea is that instead of pushing more and more current towards the base of Q1, I will commutate some current through the collector of Q3. Okay, so you understand that what happens is your VBE3, that is the base emitter voltage of Q3, will be equal to I naught into RS, right? So based on that, your RS is designed for the worst case scenario, right? Because this voltage is going to come over here. You understand that VBE3 will be I naught times RS. Therefore, RS is VBE3, which may be 0.6 volts or 0.7 volts divided by IS. So based on this, there are a lot of problems which you will be seeing as well. So just remember, just understand that the base emitter across Q3 is going to appear across this RS, and you assume that this current is negligibly small than the load current. Therefore, VBE3 is equal to I naught into RS. Okay. So the idea is you get a fixed voltage till a specific rated current beyond which this transistor is going to turn on. Okay. Okay. So this was regarding the overcurrent limiting mechanism, and you also saw some improvement, right? That is how to improve it. You know that Vi is actually an unregulated Vi. Therefore, it doesn't make sense to actually have your Zener based on the input voltage, right? So instead of having the Zener from the input side, we shifted it to the output side. Zener is over here and the RZ is from the output, tapped from the output. So this ensures that your Zener voltage is fixed. And the second thing that we did was we saw that this IB was a constant current source. So we actually implemented a constant current source. So we just saw the implementation of a constant current source using shunt regulator. So you see that using a shunt regulator, we implemented a constant current source instead of IB. Okay. Right. So this was using BJTs, and a more efficient way would be to use an op amp, and a simpler way as well. So you have the op amp, which with its positive terminal getting the VZ, Zener voltage, and the negative terminal getting the tapped output voltage. So this is your reference VZ, and AV naught is your actual. So you compare both of them using an op amp, and let's say it operates in the differential mode. It will take an appropriate action based on the difference between both of these, and it will you sink a current or you source a current from this op amp. It will control your BJT over here. Okay, and of course you can incorporate your overcurrent protection circuits as well over here to ensure that the circuit operates properly. What you do is you tap your V in and you have a diode over here. This ensures that during starting, since your V naught has not yet built up, the circuit has to operate, right? So during starting, you take a tapping from the input and give it to the plus terminal of the op amp. However, if once your output builds up, your VZ becomes more than your V in, therefore this diode goes into reverse bias mode, right? Okay. So till this point, if you have any doubts, you just type in the chat box if you have any doubts, or else we can go to problems. Yeah, so hi Akshat, can you tell the specific circuit that you want help with? Or it will be better if we can recapitulate it again for you towards the end of this class after we see the problems. Okay. And between, if you want with help with any circuit, you can just write in the chat box. Okay. You just write it in the chat box for this specific circuit. Okay. So let's go to the first problem. Today we only have 12 problems, so it will be over relatively faster. So we'll just jump right into it. The current limiting circuit is given below. Let me take my pointer. Calculate the RS resistance in milliohm so that rated load current of 10 ampere can be limited. Okay, so this is the circuit that we just saw, right? This is a series regulator. You understand that this is a series regulator. You understand that you have BJT over here and then an RS. And the design criteria for RS that we just saw was that your VBE3, right? It is going to appear across your RS, right? And so when will this circuit kick in to operate? That is, when will this Q3 start conducting? This Q3 should start, ideally, this Q3 should start conducting if your current increases beyond the maximum current rating, correct? If your current increases beyond the maximum current rating, you want this to operate. Okay. So the idea is, so when will this BJT start conducting? This BJT will start conducting if your base emitter voltage or the voltage across your base and emitter goes beyond zero point 0.6 or zero point 0.7 volts, whatever is the VBE, right? So whatever is your VBE for this Q3, if your voltage across base to emitter goes beyond that, only then this path will start conducting, right? So you want this part to start conducting for current protection or current protection, right? So under normal circumstance, this BJT should not conduct. That is, under normal operation, this BJT should not conduct, right? So you design your RS based on this criteria. That is, VBE is equal to I naught into RS. This is the maximum at the rated load condition or the rated condition. So the I naught rated VBE is 0.6 volt. You design your RS so that this will start conducting beyond that point. Okay. So with that as the motivation, hope you understand what we are doing. With that as the motivation, they have given VBE is equal to 0.7 volt. Okay. And rated load current is 10 ampere. So 10 ampere flows over here. So what is the RS resistance that you need to put so that rated load current of 10 ampere can be limited? So up to 10 ampere, it can flow through this RS, right? So how do you do that? Your VBE will be equal to I naught into RS, correct? So I naught into RS is equal to your VBE. Therefore, your RS is equal to VBE by I naught rated. That is 0.7 by 10. That is 0.07 ohms or 70 milliohms. Okay, simple, right? So this is a very straightforward question. That is, your base emitter voltage should be equal to your I naught into RS. So I'll just give you 2 minutes time for each question so that if you want, you can just have a look at this. We can go a little, relatively slow today. So you can just have a look at this. Okay. So the given series regulator has the following parameters. That is, Vn is 25 ohms, R naught load resistance 15 kilo ohm, Vz is 2.4 volt, right? And RB is 18.6K, RZ is 452K. Okay. For Q1, HFE sat or beta that you might call, or the current gain is 50. VCE1 is 10 volts, VBE1 is 0.7 volt, and for Q2, it is again given VB the beta 2 is 200 and VBE2 is 0.6. So For the series regulator, what is the value of X? That is X is equal to R2 by R1 plus R2, right? They have also defined it. That is the ratio that or the tapping ratio. So the question is, what is the tapping ratio? Correct. So tapping ratio can be obtained from this, from seeing the circuit itself. You can understand that Vx or VR2 applying KVL in this loop that I show in my pointer. You understand that Vx is simply VBE plus Vz, right? VB and Vz together, that will give you Vx. And V naught is the voltage across the load, that is I naught into R naught. Okay. So with this information, you should be able to get, right? That is, your Vin is given Q1, VCE1, you know. Therefore, you will know what is I naught into R naught. Okay. Yeah. So we'll just go here. You see that V naught, by applying KVL in this outer loop, you understand that V naught is equal to Vin minus VCE1. Correct? V naught is equal to Vn minus VCE1, right? So your Vn has been given as 25. Vn is 25, VCE1 is 10. Therefore, V naught is going to be 15 volt, right? 25 minus 10 is 15 volt. That is your V naught. And what is Vx? Vx can be calculated from KVL over here. That is Vz plus VBE. That is 2.4 is given as Vz. You understand that Vz is 2.4 volt. So 2.4 plus 0.6. It's your Vx, that is 3 volt. Therefore, your ratio is equal to Vx divided by V naught, right? X is equal to R2 by R1 plus R2 or Vx divided by V naught. So 3 by 15, right? That is 0.2. Okay. So it is simply KVL in the outer loop and KVL in the inner loop. Okay. So this is again a very simple question. You can just have a 1 minute look at it, and all the parameters over here are already given in the circuit or given in the problem. Okay. So simply KVL application fetches you the answer. Okay. So just have a look at this. Okay, so we'll just move ahead with the next problem. So what is the efficiency of the current regulator circuit below? So you understand that this is a current regulator circuit. Okay, so they are asking about the efficiency of the circuit. Okay, so current regulator, it's based on the shunt voltage regulator. You have the Zener diode over here and the series resistance RS over here. Okay, and you have the BJT and then you have the load. Okay, so what is the efficiency? Right? So what will be the efficiency? Efficiency will be simply P naught by P in, that is the output power divided by input power. Output power is obtained across the load. That is, you need to find V naught into I naught, or so V naught into I naught. V naught is given as 4 volt. You just need to find out what is I naught. Okay. What is your I naught? I naught is simply your emitter current, or sorry, your collector current, right? So collector current into 4 is your output power. And what is your input power? Input power is VCC 15 volt into total current, that is IZ plus IE, right? So IZ plus IE into 15 is your input power and 4 into IC is your output power. You just need to calculate the currents and you get the answer. Okay, fine. So one thing is we need to find out about this IN4739 diode, right? So they have just mentioned the diode part number. We need to go to its data sheet and find out what is IN4739. Let me see if I'm there. Yeah. So let me go to the internet and IN4739. Right. So it's a diode from Fairchild and yeah. So you go over here, they have given the dissipation as 1 watt and yeah, 4739 is over here. You see that your typical value of VZ is around 9.1 volt, right? 4739 is around 9.1 volt. So we have taken, you can see the highlighted portion in my laptop as well. So we will take 9.1 volt as the VZ for further calculation. Okay, right. So this is 9.1 volt. That is the voltage across the Zener is 9.1. Total voltage is 15. Therefore, you know what is the voltage across this 300 ohms, right? 15 minus 9.1 is the voltage across 300 ohms. Correct. So it's a 9.1 Zener. So current through the 300 ohm resistor is simply the voltage across it. That is 15 minus 9.1 divided by 300, right? Yeah, 15 minus 9.1 divided by 300. That's your current through this 300 ohm resistor, right? That is 9.7 milliamps. Okay. And using KVL in this loop, right? So you understand that VZ over here is equal to IERE plus VEB. That is in this loop. If you apply KVL over here, VZ is equal to IE into RE. That is IE into 10 ohms plus VBE. That is minus 0.75. Okay. So you find out what is IE, right? IE is found out from this KVL itself. So IE is simply VZ 9.1 minus VEB, that is 0.75 divided by 10, that is IE turns out to be 0.835 amps. Therefore, the base current is simply obtained by the beta relationship, that is IB is equal to IE by 1 plus beta, right? That is 9.7 milliamps. That is your base current. So this is your base current and your 300 ohm current is also known. Your base current is known. Therefore, you can calculate what is your IZ, right? So, yeah. The current through Zener is therefore given by um, the difference between this current and this current, right? That is 10 milliamps. This is your current through this Zener diode. Okay, right? So you just found out what is the current through Zener diode, and furthermore, you also know what is your VEC, right? By applying KVL in this loop, right? 15 minus IERE minus VCE minus ICRC equal to 0. Therefore, you know what is your VEC, right? You know what is your VEC. And since your VEC is known, you can find out what is the total efficiency from this. That is, the current through the load is given by IB into beta. So IC is known. So the efficiency is V naught I naught divided by V in I in. That is V out into I out. That is V out is 4 and I out is simply 0.824. That is the collector current, right? Divided by VCC into IZ plus IE, right? That is IZ is simply the Zener current that we just found out earlier plus IE. Okay, that is this current. Turns out to be around 26%. Okay, right. So in just what did we do over here? So in this question, we just found out what is the VZ of the Zener diode that is given. Okay. Once we found out what is Zener diode's VZ from its data sheet, we found out what is the current through the 300 ohm. Okay. And you applied KVL in this loop, inner loop, you find out what is IE, right? That is the emitter current. Since you know what is IE, you know what is IB and IC as well, using the beta relationship. Okay. So IB is equal to IE by 1 plus beta, IC is equal to IC is equal to beta times IB. Okay. So from that, you know what is your IB and IC as well. Okay. So this will give you the answer, right? That is, you know what is the current through Zener. By applying KCL over here, you get this current minus this current. Okay. And the current through the load, you also get as IC. Therefore, the efficiency is V naught I naught by V in I in. V naught I naught is VC into IC, and V in I in is VCC into IZ plus IE, 26%. Okay. Yeah. Yeah, so I'll just pause a minute over here. You just process this question and then we will go ahead. Okay. Simply apply KVL, right? And you get the answer. KVL and KCL, and yeah, you get the answer. Okay, so uh, we can go on to the next question. If the input voltage ranges from 20 volt to 30 volt and the Zener breakdown voltage is 5 volt, okay, so input Vs can range from 20 to 30 and the Zener breakdown voltage is 5 volt, okay, Zener dynamic resistance, that is Rz, is 2 ohms. Find the minimum value of output voltage V naught as indicated in the circuit below. So to find out the minimum voltage, you need to consider the minimum input voltage as well, which is very much intuitive. Okay. Yeah. To find the minimum value of the output voltage, we will take the lower limit of the input voltage, which is 20 volts, right? 20 to 30 is a variation. Therefore, um, you take the lower limit as 20 volts. Therefore, the equivalent circuit becomes something like this. 20 volts over here, 200 ohms, and you replace the Zener diode with its non-ideal circuit, right? That is the Zener voltage 5 volts and its RZ, that is 2 ohms. Okay, right? So this is very much obvious for us. Okay, so now that we have the circuit, just apply KVL and you get the answer, right? So what we will do is we will consider this current going from point A to point B as I1. The Zener current is I2. Therefore, the total current will be I1 plus I2. We will just have two variables because we have two unknowns over here. Apply KVL, that is first in this loop, that is in the inner loop. So you get by applying KVL, you get 15, that is Vs is equal to 200 into I1 minus 2 into I2, right? That is equal to 15. How it is 15? Vs is 20 and here you have 5. So 20 minus 5 is 15. Okay. So this is KVL in the inner loop and you apply KVL in the second loop, right? That is 1K into I1 plus I2, correct? That is equal to 5. That is in this loop. That is 1K into I1 plus I2 and then you have plus I2 into 2 is equal to 5 volts. Okay. So now you understand that you have two equations, a set of two linear equations with two unknowns. You can just solve them and you get what is I1 and I2. If you get what is I1 and I2, you know that V0 is equal to the load resistance into I1 plus I2. That is V0 is equal to load resistance into I1 plus I2 and it turns out to be 5.14 volts. Okay. So this is again a pretty simple problem. I'll just give you a minute over here. Yeah, so the input voltage range variation is given. It varies from 20 to 30 minimum to maximum. The non-ideal resistance of Zener diode is given. Its drop is also given, and find the minimum value of output voltage. So yeah, for minimum value, you take the minimum input voltage and just apply KVL using the non-ideal model of the diode, Zener diode, and you end up with the answer. Yeah, sorry about that. My laptop went out of charge and so I got locked out. Just a second. I'll just share my screen once again. Yeah, so I'll just start off once again. Yeah, so we were over here. Okay, so just have a look at this for a minute and we will proceed to the next question. Okay, so yeah, so which of the following statements is valid for the foldback current limiting circuit? Short circuit current limit can be set lower than the rated load current. Short circuit current limit can be set higher than the rated load current. Short circuit current limit cannot be altered using foldback current limiting circuit. And short circuit current limit is the same as load current, rated load current. You know that the answer for this is? So can anyone tell the answer? Anyone try to attempt the answer? So in a foldback current limiting circuit, what is the load, what is the short circuit current limit? Can it be lesser than the load current or higher than the load current or what? Based on the lecture slides itself, I think it is very obvious. So in a fallback current limiting circuit, okay, so the answer is that in a fallback current limiting circuit, the short circuit current limit can be set lower than the rated load current. You would have studied something like, okay, today I don't have the pen, so I can't really draw over here, but you would have studied that the current limit is something like, yeah, so the current limit is something like you maintain a fixed V naught till I rated and it comes down something like this. Okay. So yeah, so this is your I rated and over here this is your short circuit current limit. Okay, so you can actually set a lower short circuit current limit for the fallback current limiting circuit and that's your advantage. So once it exceeds I rated, it will go back to a current limit which is lesser than the short circuit current limit. Okay, fine. Okay, so next question is choose the linear regulator from the table that satisfies the following. So input voltage range is given 16 to 24 volts VDC. Output voltage adjustable range is 8 to 12 volts. Okay. Recommended inherent current handling capability is it should be able to handle 4 amps continuous current. And of course, its temperature coefficient is less than or equal to 2%. Line regulation is less than or equal to 0.5%. And finally, the load regulation should be less than or equal to 0.5%. Okay. So in this table, they have actually given you 4 commercially available regulators. Okay. Commercially available devices. You need to choose which of the following best fits the given specifications. Okay. Fine. So, yeah. So from the given parameters, you understand that the max recommended current handling capability should be 4 amps continuous, right? That means that LM317 cannot be used, right? Because LM317 has a current rating of only 1.5 amperes, you need 4 amps, right? So LM317 is not the answer. Okay. Next, come to line regulation. Line regulation should be less than or equal to 0.5 percentage, right? And all of these are less than or equal to 0.5 percentage. So you still have LM138, LM1084, and LMS1585A, right? Okay. And come to load regulation, should be less than or equal to 0.5 percentage. Okay. Again, you see that LM317 cannot be used because it has a load regulation of 1.5 percentage, which is higher. Okay. Okay. And finally, temperature coefficient should be less than or equal to 2 percentage. You see all of them actually satisfy the criteria, right? So you are still left with 138, 1084, and LMS 1585A. Okay, fine. And what about the input output voltage differential, output voltage differential maximum? So the required value is over here. You see, input can range from 16 to 24, output can range from 8 to 12, right? So you take the worst case scenario. Worst case is high input voltage and very low output voltage. So high input voltage of 24 volts and very low output voltage of 8 volts, right? So the differential is what? 24 minus 8. 24 minus 8, that is 16 volts. Okay, it should be able to handle at least 16 volts. Therefore, you see that the last one, LMS1585A, is eliminated because it can handle only till 13 volts, but we need 16 volt. That is a maximum, right? So now you are left with only two options, LM138 and LM1085. Okay, 1084, sorry. And here, then you see the next one, input output differential voltage minimum. So what is the minimum? That is minimum is that is minimum value of input and maximum value of output. That is the difference is very small. Okay, that is 16 volt at the input and 12 volt at the output. That is 4 volts. So you see that both of these can do the job, 3 volt and 1.5 volt. However, since it can tolerate a very minimal input output differential, you will want to choose LM1084. Okay. Yeah. So that is what we were just seeing from the specification. This is what is required. More than or equal to 4 amps, less than or equal to 0.5, less than or equal to 0.5 load regulation, less than or equal to 0.5 line regulation, less than 2% temperature stability, and worst case differential is 16 volt, that is 24 input and 8 volt output, and the other end, that is the minimal differential, is 16 volt input and 12 volt output. So which of the following satisfies means you understand that 1084 is able to satisfy all of these, right? Okay. Okay. So at this point, I'll just take a pause for 3-4 minutes and then we can resume once again. Okay. Yeah, so we will just start again. So in the figure below, a snippet of the typical application circuit of LM317IC is shown from the datasheet of LM317 TIIC, Texas Instruments IC. Using this circuit, find the value of the variable resistor R2 in kilo ohms, right? To obtain V naught equal to 10 volt. So your V naught over here, let me take my pointer. V naught is 10 volt. Okay. Find out what is R2. That is a question. Okay. R2 we need to find out. R1 is given. R1 is the voltage across or your output to adjust pin. That is Vref. Vref is 1.25. Okay. You understand that this is simply a resistive divider circuit, right? So your V naught is 10. Okay. R1 is 1.25. So you will know what is VR2. Okay, R1 is given. You just need to find out R2, right? So it's a very simple circuit, correct? Yeah. So you see that since your V naught is given as 10 volt, okay, and Vref is 1.25, you know that by applying KVL over here, right? You apply KVL, V naught is equal to Vref plus VR2, correct? So from that you can obtain what is VR2, okay? Okay, so once you know what is VR2, right? VR2 is simply I into R2 and VR1 or is equal to Vref, that is 1.25 volt. Okay, so from this itself you can calculate, since R1 is given as 240 ohms, you can know what is R2. Okay, simple problem, right? Again, so you just observe that this is simply like a resistive divider circuit across V naught. V naught is 10. You take a tapping of 1.25. Therefore, the voltage across VR2 will be the rest half of that. So based on that, you can do. Okay. Or R2 by R1 is 7. Correct. Because Vref is 1.25. The total output is 10. Vref is 1.25. Therefore, the remaining, that is 8.75 volts, appears across R2. Okay. So corresponding to 1.25, you have 240 ohms. So corresponding to 8.75, you just need to find out. And it turns out to be around 1.68 kilo ohms. Right? Again, a very simple problem. You can just have a look at this, but yeah, this is simply a resistive divider circuit. R1 is given, Vref is given, V naught is given. Okay, just find out what is VR2, and since VR2, I mean, since your VR1 and R1 are directly proportional, so VR1 by VR2 is equal to R1 by R2. Okay, from that you can find out what is R2. Turns out to be 1.68 kilo ohms. Okay, yeah. Okay, so I'll just wait for a moment and then we can go. The next question. Okay. So based on the information provided in question 7, that is the previous question, find the maximum value of thermal resistance from junction to ambient in degree per watt for load current I naught equal to 1 amp. So V naught was already there. So I naught is being given as 1 ampere. Input current is also given, that is 1.5 amperes. V in is given as 15 volt. R2 by R1 is 3. Now they have changed R2 by R1. R2 by R1 is 3. The ambient is 25. So and your maximum junction temperature needs to be less than 100 degrees. So what is the thermal resistance that you have so that your junction temperature is 100 degrees? Okay, so let's go back to the circuit once again. So you see that in this circuit, R2 by R1 was given as 3, right? R2 by R1 is 3. Therefore, your V naught will be simply this Vref, that is 1.25 into 1 plus R2 by R1. Okay. Again, you need not have to see this formula every time. Just apply KVL. Okay. So your R1 VR1 is given 1.25 and R2 by R1 is also given, that is 3. Therefore, since VREF is 1.25, VR2 will be 3 times this, right? That is 3 into 1.25. Therefore, the total summation will be 1.25 plus 3 into 1.25. Correct? That is why it is 1.25 into 4, that is 5 volt. Okay, simple, right? It's just KVL. Okay, so this is V naught. So what is the total power loss? Pi minus P out, right? That is input power minus output power. Input power is Vi into Ii, that is input voltage into input current, and output power is V naught into I naught. Okay, so Vi and Ii are given in the question. That is Vi 15 volt and Ii is 1.5 amperes. Okay, 15 into 1.5, and output power is V naught into I naught. Okay, I naught is given as 1 ampere, and we just calculated that V naught is 5 volt, right? Therefore, the total power loss is input power minus output power, which is 17.5 watt. Okay, just calculate the output power or the power loss. So once you know the power loss, you know that you know this particular relation that relates your ambient temperature to the junction temperature, right? That is the difference in temperature or the temperature rise that is due to the power loss P. Okay, so therefore your Tj is equal to Ta plus P into R theta. Okay, from this you need to find out what is your R theta. Okay, it turns out to be 4.29 degree per watt. Okay, so what did we do in this question? We just calculated what is the power loss in this IC, that is input power minus output power, and you know to calculate what is the V naught, that is Vref is given 1.25, R2 by R1 is given. So R2 by R1, since R2 by R1 is 3, so the voltage across R2 will be 3 times Vref, right? So V naught will be this voltage plus this voltage. Okay, right. So this is the power loss across this element. So then, based on this particular relation, you find out what is the R theta. That is Tj is equal to Ta plus P into R theta. Okay. So I'll just hang on for a minute over here, and you can just go through it. I'll just go through the slide for you guys to understand. Yeah. So this is for the circuit previously. So we just found out what is V naught, right? And you needed to find out what is R2 by R1 and R2. Okay, just from KVL you were able to determine that, and then in this question the input and the output voltages and powers were found out. Okay, found out V naught and power loss was found out, and finally based on this, based on the power loss, you found out what is the junction temperature rise and the corresponding R theta. Okay, I'll just give you a moment over here. I'll just have some water, just a second. Yeah. So we'll just yeah. So in KVL you don't take the capacitor value. The reason being that you assume that capacitor is a voltage step element, therefore the voltage across that is actually fixed. So you assume that it's essentially a voltage source under steady state. Okay. Okay. So we will go on to the next question. In the current limiting circuit shown below, find the value of Rs plus R2. That is, let me take my pointer again. So Rs, right? And then R2. So Rs plus R2 needs to be found out in kilo ohms to limit 1 milliampere of load current for the condition when Vin is 18 volt, Vz is 4.4 volt, right? Vin is 18, Vz is 4.4, Vb is 0.6, V0 is 10 volt, and R1 is 1K. Okay, so again a pretty simple problem. That is, from this observing itself, you can tell that V0 is 10 volts and R1 is 1K, right? So, and you also know what is Vz, right? Vbe is given as 0.6. So you know what is VR2, right? By applying KVL in the inner loop, you know what is VR2. VR2 is simply this voltage and then this voltage Vz, right? So Vz, VR2 is simply Vbe plus Vz, right? That is 4.4 plus 0.6. That is your VR2. So VR2 is 5 volt. Okay. So V0 is 10, right? V0 is 10 and VR2 is simply this voltage plus this voltage, which is 5 volt. Therefore, voltage across VR1 will also be 5 volt. It's a resistive divider. So this is 5, this is 10. Therefore, VR1 is 5, right? Just we applied KVL over here. So VR1 is 5. Since VR1 and VR2 are same, therefore the resistances must be same in a resistive divider. Therefore, R1 is 1K, therefore R2 is also 1K. So R2 has been determined to be 1K, right? And what about RS? We just found out in the first problem itself that this in the current limiting circuit, your VBE is equal to I0 into RS, right? Therefore, VBE is 0.6, I0 is 1 milliampere. Therefore, RS will be 0.6 by 1 milli, or that is 6 kilo ohms, correct? So yeah, we'll just go to the problem again. So you understand that this point over here is actually 5 volt. Why? It is VBE plus VZ. That is VZ plus VBE is equal to 5 volt. Okay. So you understand that R2 and R1 are going to be same. That is 1K and 1K. Okay. And what about RS? RS is equal to VBE divided by rated current 0.6 divided by 1 milli, right? That is 600 ohms or 0.6 kilo ohms, correct? 0.6 kilo ohms. Therefore, the total current will be R2 plus RS, which is 1K for R2 and RS is 0.6K, correct? That is the current limiting circuit. You understood, right? So one was just KVL in this loop to get R2, and the other one was a current limiting circuit. That is VBE is equal to I0 into RS. Okay. Just go through this for a moment. And in a minute, we will switch on to the next question. Again, a very simple problem, right? Just you need to calculate what is R2 and RS. Just apply KVL, you get the answer. Okay. 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 So we'll just move on to the next problem. So input voltage of the series regulator circuit given varies from 20 to 25 volts. Okay, so V in varies. R1 equal to 10K. Okay, this is your R1, which is 10K. Maximum value of resistor R2. So what is R2? Okay, and the other values are given. That is the diode forward drop is 0.7. The Zener voltage is 5.1 volt, and the VB of Q1 and Q2 are 0.6 volts for both, and the output voltage is 15 volts. Again, all of these circuits can be solved by simple KVL. So now you understand one thing from the previous slides itself. We saw that during starting we have this diode, but later on this diode goes out of the picture, right? That is, if your VZ is 5.1 volt, then the um, voltage at R2, right? It should be much higher than 5.1 during starting. Okay. I mean, during starting, you understand that this voltage will come over here and there is no IZ to maintain the VZ. Okay. So you understand that the voltage at R2 should be lesser than VZ. Correct? So you just apply KVL in this loop over here. VR2 is equal to what? VR2 is equal to VD1 plus VZ, right? So your VD1 is given and VZ is also given, correct? So from that you find out what is VR2. R1 is given. So yeah. So D1 is during the startup of the circuit, that is when there is no output voltage to support this VZ, what will happen? This diode will be forward biased. Therefore, this op amp will start operating and this Q1 will come into picture. Okay. So point is this diode should no longer come into picture during steady state, right? Therefore, VR2 should be lesser than your 5.1 volt. Okay, therefore the maximum voltage over here should be how much? It should be 0.7 plus VZ, KVL in this loop. Okay, that is 5.8 volt. Okay, KVL in the lower loop. So maximum input voltage has been given as 25 volts. If you go back to the question, maximum input voltage is 25 volts. So what is the maximum value of resistor? Therefore, to find out the maximum value of resistor, we are taking the maximum input voltage. So the maximum input voltage is 25 volts. So you understand that 25 is actually getting split using this resistive divider. You just saw that VR2 should be 5.8 volt, right? VR2 is 5.8 volt in this KVL loop. Input voltage is 25 maximum. Therefore, just by applying the voltage division rule, you get what is R2. Since R1 is given as 10 kilo ohms, R2 turns out to be 3 kilo ohms. Okay. Again, a very simple question, right? That is, just apply KVL in this lower loop. You get what is VR2, and then this just a voltage divider. Therefore, you get what is R2. R1 has already been given as 10 kilo ohms. Okay. Yeah. So just I'll pause for a moment and you can see. Yeah, I'll just okay. So if you don't check the channels. Okay. Why R2 equal to R1? I guess you are asking the previous problem. So in the previous problem itself, the reason R2 equal to R1 is that, see over here, output voltage is 10 volt. Okay. Then you applied KVL in this lower loop, Okay. So what is VR2? VR2 is VBE plus VZ. Okay. VB is 4.4 and VB is 0.6 and VZ is 4.4. Therefore, VB plus VZ turns out to be 4.4 plus 0.6, which is 5 volt. So 5 volt across this. V0 is 10. VR2 is 5. Therefore, this is also 5. Therefore, R1 and R2 must be same. Correct? Neglecting any current shunting out through this base current is very small. Therefore, this and this are supposed to be same. Okay, R1 and R2 are same. Since R1 is given as 1K and the voltages are same, therefore R2 should also be 1K. Okay. Okay. So um, Yeah, so we were over here, and again the condition is we applied KVL in the lower loop, in this loop. So you obtained what is R2, R1 is given, therefore by voltage division rule you get what is R2. Okay. Okay, so referring to question number 10, the output power rating of the regulator is 5 watt. Okay, output power is 5 watt. If the overload capacity of the regulator is 1.5 times the rated power, that is output power is 5 watts. Okay, and the overload capacity is 1.5 times the rated power. The value of RS is how much? So this is your RS. Okay, so the output power is 5 watts. So you saw from the question that output voltage is 15 volt, right? So 15 volt. So what is your output power? Output power will be 15 into I naught, correct? So output power is 5 watts. Therefore, your output current will be P naught by V naught, which is 5 by 15. 5 watts divided by V naught is 15. So 1 by 3 amperes. So since the regulator has an overload capacity of 1.5 times the rated power, it means that instead of 1 by 3 amperes, it can support 1 by 3 into 1.5. It has that much capacity. Okay. So maximum current will be how much? Maximum current will be 1.5 times this current, right? That is P naught is 5, V naught is 15. Therefore, I naught is going to be 1 by 3 amps, right? And since it has 1.5 times the rated load capacity, overload capacity, therefore the maximum current will be 1.5 into 1 by 3, that is 0.5 amps, right? So this is your maximum output current it can support. So you need to support you need to design your RS for the maximum output current, right? That is 1.5 times the rated power. So again, do the same thing. VBE is equal to I naught into RS, or I rated into RS. So VBE is 0.6, therefore RS is equal to 0.6 divided by whatever is the maximum current. Maximum current is 1.5 times 1 by 3, that is 0.5 amps. Okay. So RS is equal to 0.6 by 0.5, which is 1.2 ohms. Okay. So I'll just hang on in this slide for some time. You see, output current is calculated as P naught by V naught. V naught is already given in the question, 15 volt. Okay. P naught is 5 watts. So I naught is 1 by 3 amps. And it is given that the regulator has overload capacity of 1.5 times the rated load. Therefore, the maximum output current is 1.5 into I naught. Okay, that is 0.5 amperes. Yeah, so I'll just hang on here for a minute and then we can go on. Okay, yeah. So probably the last question, which one is or true from the following statements about Zener shunt regulator? Power rating of Zener diode is decided based on maximum load condition. Power rating is decided based on the no load condition. Maximum loading capacity of the Zener is decided based on the minimum current required to maintain the Zener in the breakdown region, and minimum loading capability of the Zener decided based on the minimum current required to maintain the Zener in the breakdown. So you can understand that if you have studied the basics of Zener diode, you will know that the power rating is decided based on the no load condition. Okay, that is B, and maximum loading capability of the Zener is decided based on the minimum current required to maintain in the Zener breakdown region. Okay, yeah. So B and C are the answers to question number 12. So this concludes today's problem solving session. So in the meanwhile, if you have any doubts, you can go ahead and ask. We saw different problems and we had a quick recapitulation of the. So in what way op amp is used here? Okay. So let's go back to some basics, right? So yeah, so this is the series regulator that you are aware of, right? Sorry, yeah, that is you want to drop some voltage across Q1, right? For that you need to effectively bias Q1 properly. That is, you need to inject or sink proper bias current to Q1, right? In order to achieve that, what you have is you have another BJT. Okay, the operation is such that this is kind of a subtraction mechanism, correct? Because at the emitter you have the V0 reference, and at the base you have the actual V0 or the tapped out V0. So what you get across VBE is actually A V0 minus V0 ref. So this is kind of the difference, right? And based on this, your base current will vary. Based on your actual voltage, base current will vary. Base current varies, your collector current varies. Since your IB is fixed, this current will also vary as the collector current of Q2 varies, the base current of Q1 varies. Since the base current varies, the drop will vary. Okay, this is the normal principle. That is, you are using BJTs. So the idea is, instead of using this BJT for subtraction, that is AV0 minus V0 ref across VBE, why not use an op amp? Op amp, is kind of a differential amplifier circuit, right? That is, you give the plus voltage and minus voltage, it can give you the difference between them, or it can act based on the difference, right? So what people have done is they have replaced Q2 with an op amp. Okay, you see over here, that is AV0 is going to the negative terminal, that is the actual voltage, and the reference 5 volt or the Zener voltage VZ is going to the positive terminal. Okay, so the difference between them, based on the difference between them, there is a base current that is injected to Q1. Simple, right? Again, the idea is you wanted to take a difference between the actual voltage and the reference voltage. You have used an op amp over here. Over there, you were using a BJT and you were controlling the current. Here, you are using an op amp and you put a resistor over here and you control the current. Okay. So that is why in this problem as well, I guess they have given that. Yeah. Yeah, in this problem as well. It's the same principle. Okay. Instead of using BJT, they have used an op amp to subtract the actual value and the reference value. Okay. Yeah. So any other doubts or yeah, okay, Akshit. Okay, so if there are no more doubts, we can hang for the day, stop for the day. So thanks for attending. So assignments are tough. So the practice problems are supposed to help that only. So let's see. Point is, all of these may seem tough, but you understood, right? Most of these problems are based on simple KVL and simple BJT logic only. Okay, you need not even know too much into operation. You just see the circuit and you can apply KVL and you will be getting the answer. Just that you need to juggle a little bit between what current to take or beta times heavy and that stuff. It's actually simple. Okay, what we did today was simple network theory only. We didn't do anything extra. Okay, simple network theory and little bit of analog. Okay. Okay, so if there are no more questions, we can close for the day. Yeah, okay. Nice, actually. Okay, so we can close for the day. Thanks everyone for attending. I will stop sharing. And now, as usual, the PPTs and the recorded lecture will be uploaded. You can go through that later as well. Okay, so I will stop my camera and yeah, so good night everyone. Thanks for attending and good night. Yeah.
କଣ କରୁଛୁ ବେ?